Somewhere between Miami, Bermuda, and Puerto Rico, the ocean holds a quiet that has swallowed more than 500 ships and aircraft since the 19th century. Vessels that slipped beneath the waves or vanished from radar screens without a single distress call, without wreckage, without explanation. This stretch of water, roughly 500,000 square miles of deep blue and sudden squalls, has carried many names over the years, though the one that endures is simple enough: the Bermuda Triangle. There is no need to chase answers tonight, only to drift alongside the stories themselves, to let the mystery exist as mysteries do, soft at the edges and full of sea air. If these longer journeys into the unknown bring a kind of stillness, subscribing means more of them will find their way to you. The water is calm now, and the story can begin. If you were to take a map of the Western Atlantic Ocean and place 3 small pins upon it, one at the southern tip of Florida near the city of Miami, another at the island of Bermuda, some 650 miles to the northeast, and a third at the city of San Juan on the island of Puerto Rico. And if you were then to draw lines connecting these 3 points, you would trace the rough boundaries of a region that has come to be known, in the popular imagination at least, as the Bermuda Triangle. The resulting shape is not a perfect equilateral triangle, as the name might suggest, but rather an elongated and somewhat irregular form that encompasses, depending on which particular boundaries one chooses to accept, somewhere between 440,000 and 510,000 square miles of open ocean. This is a considerable expanse of water, roughly equivalent in area to the combined landmass of France and Spain, or perhaps 3 times the size of the state of California. And yet, when one considers the vastness of the Atlantic Ocean as a whole, it represents only a modest portion of that great body of water that separates the Americas from Europe and Africa. The coordinates of this region place it within the subtropical zone of the North Atlantic, with the southernmost vertex near San Juan sitting at approximately 18 degrees north latitude, while the Bermuda vertex lies closer to 32 degrees north. This span of 14 degrees of latitude means that the triangle stretches across a significant range of oceanic and atmospheric conditions, from the properly tropical waters around Puerto Rico, where the sea remains warm throughout the year and palm trees line the coastal roads, to the somewhat more temperate, though still quite mild waters surrounding Bermuda, where the climate resembles that of the Mediterranean more than the Caribbean. The western boundary, formed by the Florida coast and extending northward, represents the continental shelf of North America, giving way, sometimes gradually and sometimes quite abruptly, to the much deeper waters of the open Atlantic. The depths within this triangular region vary considerably, from the relatively shallow waters of the Bahama Banks, where in some places one can see the sandy bottom only a few fathoms below, to the immense Puerto Rico Trench along the southern edge, which plunges to more than 27,000 feet at its deepest point, making it the deepest location in the entire Atlantic Ocean. Within the broader boundaries of what we call the Bermuda Triangle, and extending somewhat beyond it to the north and east, lies a remarkable feature of the North Atlantic that has fascinated mariners and naturalists for centuries, and this is the Sargasso Sea. Unlike other seas, which are defined by their coastlines and the land that surrounds them, the Sargasso Sea has no shores whatsoever, being bounded instead entirely by ocean currents that circulate around it in a great clockwise gyre. The Gulf Stream flows along its western edge, while the North Atlantic Current defines its northern boundary, the Canary Current its eastern reaches, and the North Atlantic Equatorial Current its southern extent. Within this slowly rotating oval of water, which spans roughly 2 million square miles, conditions are notably different from the surrounding ocean. The waters are unusually clear and remarkably blue, owing to the relative absence of the nutrients and plankton that cloud other seas with greenish or grayish tints. The Sargasso Sea is sometimes described as an oceanic desert, not because it lacks water, of course, but because its still and stratified nature limits the upwelling of nutrients from the depths that would otherwise support abundant marine life. The name Sargasso comes to us from Portuguese sailors of the 15th and 16th centuries, who were among the first Europeans to venture into these waters during the Great Age of Exploration. When their vessels entered this region of calm winds and gentle swells, they encountered vast floating mats of a distinctive golden-brown seaweed, unlike anything they had seen in the coastal waters of Europe. The small air bladders that keep this seaweed afloat reminded these sailors of a variety of grape known in Portuguese as salgazo or sargasso, and so they named the weed accordingly, Lee, and by extension the entire sea in which it drifted. This seaweed, which we now classify in the genus Sargassum and recognize as comprising two primary species, Sargassum natans and Sargassum flutans, is unique among seaweeds in that it spends its entire life cycle floating freely upon the surface of the ocean rather than growing attached to rocks or the sea floor. The Sargasso Sea is the only place in the world where such quantities of pelagic, that is to say, open ocean dwelling, seaweed can be found. And this creates a floating ecosystem quite unlike any other on Earth. Small crabs and shrimp, specially adapted with coloring and body shapes that mimic the weed itself, live their entire lives among the drifting fronds, while sea turtles rest and feed there during their long oceanic journeys, and certain species of eel travel thousands of miles from the rivers of Europe and North America to spawn in these peculiar waters before their larvae drift back on the currents to the continents from which their parents came. When Christopher Columbus made his historic first voyage across the Atlantic in the year 1492, his 3 small ships passed directly through the Sargasso Sea and what would later become known as the Bermuda Triangle, and his log entries from those weeks at sea provide us with some of the earliest European accounts of conditions in this region. On the 13th of September, Columbus noted that the compass needle aboard his flagship, the Santa Maria, appeared to deviate from true north, moving several degrees to the northwest of the position that would be expected based on the North Star. This phenomenon, which we now understand as the natural variation between magnetic north and true geographic north that exists at different locations around the globe, was not well understood in Columbus's time, and it caused considerable consternation among his crew. Columbus, ever mindful of maintaining morale during a voyage into unknown waters, reportedly adjusted the compass readings he shared with his men to minimize their concern, though his private logs recorded the discrepancy faithfully. A few weeks later, on the 11th of October, the night before the expedition first sighted land in the Caribbean, Columbus recorded seeing a strange light in the distance, which he described as resembling a small wax candle that rose and fell in the darkness. Various explanations have been proposed for this observation over the centuries, from bioluminescent phenomena in the water to fires lit by the Taino people on the approaching shore to meteors passing through the atmosphere. And we cannot say with certainty today what Columbus saw on that October night more than 500 years ago. What we can say is that his log entries have been cited, perhaps over-enthusiastically at times, as early evidence of unusual phenomena in this region, though of course Columbus and his sailors were traveling through waters entirely new to them, where almost everything they observed would have seemed unusual to some degree. The more prosaic reality of the Bermuda Triangle today is that it represents one of the most heavily traveled stretches of ocean anywhere in the world, serving as a crucial corridor for shipping and aviation between the ports and airports of the eastern United States, the Caribbean islands, and points beyond. On any given day, one might find dozens of cruise ships plying these waters, their white hulls gleaming in the subtropical sun as they carry tourists between Miami and Nassau, San Juan and St. Saint Thomas, Bermuda and points south. Container ships loaded with goods from around the world transit through on their way to the great ports of the American Atlantic coast, while oil tankers and bulk carriers follow established sea lanes that have been traveled for centuries. Fishing vessels work the rich waters of the Gulf Stream in search of mahi-mahi and tuna, and private yachts of all sizes make the popular passage from the mainland to Bermuda and the Caribbean, particularly during the pleasant months of spring and autumn. The skies above are equally busy, with commercial aircraft following standard routes between the major airports of the region, including Miami International, San Juan's Luis Muñoz Marin International, and the smaller but still quite busy LF Wade International in Bermuda, as well as countless smaller airfields throughout the Bahamas and the Caribbean islands. One of the defining features of the waters within the Bermuda Triangle is the Gulf Stream, that great river within the ocean that flows northward from the Caribbean, around the tip of Florida, and then northeastward along the Atlantic coast of the United States, before turning eastward to cross the open ocean toward Europe. Within the Triangle region, the Gulf Stream flows at speeds typically ranging from 4 to 5 knots, though in some areas and under certain conditions, the current may run even faster. To put this in perspective, a speed of 5 knots represents approximately 5 3/4 miles per hour, which may not seem particularly swift on land, but represents a significant force when applied to the immense volume of water that constitutes this current. A vessel adrift in the Gulf Stream could be carried 50 or 60 miles in a single day without any wind or engine power at all. And this has important implications for understanding what happens to ships or aircraft that meet with misfortune in these waters. Debris, wreckage, and even survivors can be carried great distances from the site of an incident in a relatively short time, making search and rescue operations more challenging and sometimes causing the remains of lost vessels to be found far from where they were last reported. The warm waters of the Gulf Stream, with their surface temperatures remaining above 70 degrees Fahrenheit even in winter, also play a significant role in the weather patterns of the region. And this brings us to another important characteristic of the Bermuda Triangle, which is its position within what meteorologists call the Atlantic Hurricane Corridor. The same warm tropical waters that create such pleasant conditions for tourism and marine life also provide the energy that powers the great rotating storms that form in the Atlantic between June and November each year. Many of the most destructive hurricanes in recorded history have passed through the Bermuda Triangle on their way toward landfall in Florida, the Gulf Coast, or the eastern seaboard. And even during the relatively calmer months, sudden and violent thunderstorms can develop in this region with surprising speed. The warm, moist air that rises from the Gulf Stream creates unstable atmospheric conditions that can produce waterspouts. Those oceanic tornadoes that descend from dark cumulus clouds to touch the surface of the sea in narrow spinning columns of spray. And while most waterspouts are relatively weak and short-lived compared to their terrestrial cousins, they can nonetheless pose a hazard to small vessels caught beneath them. Beyond the dramatic weather events that occasionally affect the region, there is also the simple matter of the sea itself, which in the Bermuda Triangle, as elsewhere, can be a challenging environment for human endeavors. The deep blue waters that characterize much of this region indicate the absence of a shallow bottom that might offer visual reference or places of refuge. And the distances between safe harbors can be considerable. A sailor who leaves the coast of Florida bound for Bermuda faces a passage of more than 600 miles across open ocean, with no land in between and no possibility of anchoring for rest or shelter. Weather forecasts and navigational equipment have improved enormously over the past century, making such passages far safer than they once were. But the sea remains the sea, and those who travel upon it must always respect its power and its indifference to human plans. Millions of people cross the Bermuda Triangle each year without incident, the vast majority of them aboard large vessels or aircraft that are well equipped to handle the ordinary challenges of the region. And they arrive at their destinations as expected, with nothing more remarkable to report than pleasant weather, or perhaps a glimpse of dolphins playing in the bow wave. And yet, despite all of this ordinariness, despite the cruise ships and the cargo vessels and the daily flights, something about this particular stretch of ocean has captured and held the human imagination in a way that few other places on Earth can match. The name Bermuda Triangle carries with it an air of mystery that persists even in our age of satellite navigation and real-time weather tracking. And people continue to wonder what secrets might lie beneath those deep blue waters, or what forces might act upon the ships and aircraft that pass through. In the sections that follow, we will examine the stories and the incidents that gave rise to this reputation, and we will consider, calmly and without sensation, what natural explanations might account for the events that have occurred here over the years. But for now, as we drift on the gentle swells of this warm Atlantic current, let us simply appreciate that we are in a place where the ocean meets the sky in an endless blue horizon, where the floating sargassum weed rises and falls with the breathing of the sea, and where the same waters that carried the ships of Columbus still carry the vessels of our own time, century after century, toward destinations both near and far. On the 5th of December in 1945, the afternoon light was still bright and clear over the eastern coast of Florida, and the air carried that particular quality of warmth and softness that often settles over the Atlantic coastline in early winter. The conditions were, by all accounts, rather pleasant for flying, with visibility extending for many miles and the sea below appearing calm and glittering beneath the subtropical sun. It was the sort of day that would have seemed unremarkable to the young men preparing for their afternoon training exercise. A routine matter of navigation and practice bombing runs over the shallow waters of the Bahamas, the kind of exercise they had performed many times before and would have expected to perform many times again. At 14 minutes past 2 in the afternoon, 5 TBM Avenger torpedo bombers lifted from the runways of Fort Lauderdale Naval Air Station and climbed steadily into that gentle December sky. These were substantial aircraft, each one a single-engine craft with a wingspan of just over 54 feet, designed during the war years to carry torpedoes and bombs against enemy vessels. Though, on this particular afternoon, they carried only practice ordnance and the weight of their 3-man crews. The formation was designated Flight 19, a thoroughly ordinary designation that would have meant nothing special to anyone hearing it announced over the radio that day. And yet, it is a designation that has since become one of the most frequently discussed in the long history of aviation. Lieutenant Charles Carroll Taylor was the flight leader that afternoon, an experienced pilot who had accumulated some 2,500 hours of flight time, including combat missions in the Pacific during the war that had ended only months earlier. He was 28 years old, a capable aviator by all accounts, though he was relatively new to this particular stretch of Florida coastline, having transferred to Fort Lauderdale only recently from Miami. The 13 other airmen under his command ranged in experience from seasoned veterans to students still learning the complexities of naval aviation. And together they formed a group of 14 souls who climbed into those 5 grey aircraft with no particular sense that this afternoon would be any different from the countless training exercises that had come before. The planned route was a familiar one, known as Navigation Problem Number 1, a triangular course that would take the flight east over the ocean to an area called Hen and Chicken Shoals, where they would conduct practice bombing runs, then north toward Grand Bahama Island, and finally southwest back to Fort Lauderdale. The entire exercise was expected to take approximately 2 hours, returning the aircraft to base well before sunset, with plenty of fuel remaining and plenty of daylight in which to land. The weather briefing that morning had indicated favorable conditions throughout the afternoon, and there seemed no particular reason for concern as the 5 Avengers disappeared into the eastern sky. For approximately 90 minutes, the flight proceeded without incident. The aircraft reached the target area, conducted their bombing practice over the shoals, and appeared to be following their planned course northward. It was sometime after 3:30 in the afternoon when the first indications of difficulty began to emerge, carried over the radio waves in fragments of conversation that would later be pieced together by investigators trying to understand what had occurred. Lieutenant Taylor's voice came across the radio to the Fort Lauderdale tower, reporting that his compasses were not functioning properly, that both of his directional instruments appeared to have failed, and that he was uncertain of his position over the ocean. This was unusual but not immediately alarming, as compass malfunctions were a known phenomenon in aviation, and the standard procedure in such circumstances was to fly westward until reaching the Florida coastline, whereupon the pilot could follow the coast back to base. The sea and the sky tend to look rather similar in all directions when one is flying over open water, And without a functioning compass, a pilot must rely on other reference points: the position of the sun, the appearance of landmarks below, or radio guidance from stations ashore. What followed over the next several hours was a series of radio transmissions that painted an increasingly concerning picture of confusion and disorientation. Taylor reported that he believed the flight had somehow drifted over the Florida Keys, the long chain of islands extending southwest from the Florida Peninsula, which would have placed them far to the west of their intended course. If this were true, the appropriate action would be to turn northeast to reach the mainland. However, other pilots in the formation, who could hear Taylor's transmissions, appeared to disagree with this assessment, and there are indications in the fragmentary radio records that at least some of the student pilots believed they were actually over the Atlantic, east of Florida, in which case a westward heading would be the correct choice. The senior flight instructor at Fort Lauderdale, upon hearing of the situation, suggested that Taylor turn over command to one of the Marine pilots in the formation if he was unable to determine their position, but Taylor declined to do so as the afternoon wore on and the sun began its descent toward the western horizon. The situation grew more serious, not because of any immediate mechanical emergency, but because of the simple and inexorable mathematics of fuel consumption. Each Avenger had departed with enough fuel for approximately 5.5 hours of flight, which meant that by early evening the aircraft would begin running dry, one by one, regardless of whether they had found their way home. The radio transmissions became more difficult to receive as the hours passed, partly because of increasing distance, partly because of atmospheric interference, and partly, perhaps, because the aircraft were descending closer to the wavetops as their fuel dwindled. At various times during the late afternoon, different shore stations along the Florida coast reported hearing fragments of communication from Flight 19, though the signals were often weak and broken, sometimes fading out entirely before a complete message could be understood. One transmission that has been frequently cited in accounts of the incident came at approximately 4:25 in the afternoon, when Taylor was heard to say that they would fly west until they hit the beach or ran out of gas, an instruction that suggested he had finally accepted that they were east of Florida rather than over the Keys. Yet even this decision, sensible as it might have been, was complicated by the deteriorating weather conditions. Though the morning had been calm and the early afternoon pleasant, by late in the day the winds had increased significantly, and the seas below were building into rough, white-capped swells that would make any water landing extraordinarily hazardous. The final confirmed transmission from Flight 19 came at approximately 7 in the evening, when Taylor's voice was heard reporting their position as somewhere in the vicinity of coordinates that would have placed them well out over the Atlantic, still many miles from land. After this, there was silence, broken only by occasional fragments of static and indistinct sounds that might have been voices or might have been nothing more than the random noise of the radio spectrum. The 5 aircraft, the 14 men, the hundreds of miles of open ocean beneath them, all of it receded into darkness as the brief December twilight gave way to night. The disappearance of Flight 19 prompted an immediate and extensive search operation, one of the largest air and sea rescue efforts mounted in peacetime up to that point. Ships and aircraft from multiple naval stations converged on the waters east of Florida, scanning the darkening waves for any sign of wreckage, for the yellow life rafts that each Avenger carried, for the flashing signal lights that the airmen would have activated if they had managed to ditch safely. Among the aircraft dispatched to join the search was a PBM Mariner flying boat, a large twin-engine patrol aircraft with a crew of 13 men, which departed from the Banana River Naval Air Station at approximately 7:27 in the evening. The Mariner was well suited for extended searches over open water, with its ability to land on the ocean's surface if necessary, and its substantial fuel capacity allowing it to remain airborne for many hours. However, the aircraft type was also known by a somewhat ominous nickname among the crews who flew them, a reference to the tendency of fuel vapors to accumulate in certain areas of the aircraft's hull. Whether this characteristic played any role in what occurred that night remains uncertain. But what is known is that at approximately 7:50 in the evening, a merchant vessel in the waters east of Florida reported observing a bright flash of light in the sky, followed by flames falling toward the ocean surface. The Mariner never made radio contact after its departure, never reported any difficulty, never returned to its base. When searchers reached the area where the explosion had been observed, they found a patch of oil on the water's surface and some scattered debris, but no survivors, no bodies, no wreckage substantial enough to provide any definitive explanation for what had occurred. The 13 men aboard the Mariner had vanished as completely as the 14 men of Flight 19, bringing the total number of missing to 27, the total number of lost aircraft to 6, and the total number of answers to none at all. The days that followed saw one of the most intensive search operations in American naval history, with hundreds of aircraft flying thousands of sorties over the waters between Florida and the Bahamas, and numerous ships crisscrossing the same expanse, looking for any trace of the missing men. The weather had moderated somewhat following that difficult night, but the ocean stubbornly refused to yield its secrets. Not a single body was recovered. Not a single confirmed piece of wreckage from any of the 5 Avengers. Not a life raft or a flight suit or a scrap of identification. The Atlantic, so vast and so indifferent, had simply absorbed 6 aircraft and 27 human beings and left no indication of where they might have gone. The Navy convened a board of inquiry to investigate the incident, as was standard practice following any significant loss of aircraft and personnel. The board examined all available evidence, including the fragmentary radio transmissions, the weather reports, the testimony of those who had been in contact with Flight 19 during its final hours, and the technical specifications of the aircraft involved. After considerable deliberation, the board reached a conclusion that placed the primary responsibility for the loss on Lieutenant Taylor, citing his decision to continue flying on an incorrect heading despite the suggestions of his subordinates and the guidance offered from shore stations. This finding was immediately and strenuously contested by Taylor's mother, who could not accept that her son's judgment had been so faulty as to cause the deaths of 13 other men. She argued that the Navy was simply looking for someone to blame, that the evidence was insufficient to support such a conclusion, and that her son's reputation was being unfairly damaged by a determination made on incomplete information. Her protests, sustained over a considerable period, eventually led the Navy to reconsider its findings, and in an unusual acknowledgement of uncertainty, the official cause of the incident was amended to simply state that the disappearance had resulted from causes or reasons unknown. This amended conclusion, while less satisfying in some respects than a definitive explanation, was perhaps more honest in its acknowledgement of how much remained mysterious about the events of that December afternoon and evening. The 5 Avengers had been in contact with shore stations throughout much of their ordeal, had reported their confusion and their attempts to navigate by dead reckoning, had indicated their intention to proceed in certain directions, and yet had somehow failed to reach land before their fuel was exhausted. The PBM Mariner had apparently suffered a catastrophic failure of some kind, possibly an explosion of fuel vapors, as was feared with that aircraft type. But this too remained unconfirmed. In 1991, some 46 years after the disappearance, a discovery was made that briefly raised hopes of finally solving the mystery. A salvage company searching for lost ships off the coast of Florida located 5 TBM Avenger aircraft resting on the ocean floor, their outlines clearly visible in the sonar imagery and their positions suggesting that they had come down together in relatively close proximity to one another. For a moment, it seemed that Flight 19 had finally been found, that the long decades of speculation and uncertainty might give way to definitive answers about what had occurred on that December day so long ago. However, when investigators examined the aircraft more closely, comparing their serial numbers against Navy records, they discovered that none of the 5 matched the serial numbers of the planes assigned to Flight 19. The aircraft on the ocean floor were indeed TBM Avengers. They had indeed been lost at sea, but they were from other incidents, other training accidents, other moments when the unforgiving mathematics of fuel and distance and weather had conspired against young men in military aircraft. Flight 19 itself remained undiscovered, its final resting place still unknown, its 5 aircraft and 14 crewmen still somewhere beneath the waves, absorbed into the vast and patient depths of the Atlantic. The story of Flight 19 has often been cited as one of the foundational incidents in the mythology of the Bermuda Triangle, and it is easy to understand why. The disappearance of 5 aircraft in formation, followed by the loss of a rescue plane sent to find them, followed by a complete absence of wreckage or explanation, does possess a certain quality of the inexplicable that lends itself to speculation and embellishment. Over the years, the incident has been attributed to everything from unusual magnetic anomalies to methane gas eruptions to more fanciful explanations involving phenomena that have no place in serious discussion. Yet, when one examines the evidence that actually exists, the picture that emerges is somewhat more mundane, if no less tragic. A flight leader with a malfunctioning compass became disoriented over a featureless ocean. He made decisions based on his best assessment of the situation. Decisions that may or may not have been correct, but were certainly understandable given the circumstances. The weather deteriorated as the afternoon gave way to evening. Fuel ran low and eventually ran out. The aircraft came down in rough seas, in gathering darkness, in an area that was never precisely determined and therefore could never be effectively searched. The Mariner that vanished the same night was a known fire hazard of an aircraft, and the explosion witnessed by the merchant vessel provides at least a plausible explanation for its fate. The failure to find wreckage is notable but not unprecedented. As the ocean has swallowed countless aircraft and ships over the centuries without leaving any trace that human searchers could locate. The depth of the waters in the area, the strength of the currents, the vastness of the search area, all of these factors work against the recovery of debris, especially debris that may have sunk quickly in rough weather. 27 men departed on flights that December day, 5 on a routine training exercise, and 13 on a rescue mission that became a tragedy of its own. None of them returned. None of their aircraft were ever recovered. And none of their families ever received the closure that comes from knowing precisely what occurred and where. They remain missing, officially and actually, their fates recorded in naval archives as unknown. Their names listed among the many thousands of servicemen lost at sea in circumstances that could not be fully explained. The Atlantic continues to roll over whatever secrets it holds from that day, its surface rising and falling with the same tides that have marked the passage of time since long before humans first ventured out upon its waters. Somewhere beneath those waves, perhaps scattered across miles of ocean floor, perhaps preserved in the cold darkness of the deep, the remains of Flight 19 rest in a silence that no investigation has been able to penetrate. The mystery endures, not because the explanation must be extraordinary, but simply because the evidence necessary to confirm any explanation has never been found, and perhaps never will be. And now we come to what might be called the ledger, a quiet accounting of those vessels and aircraft whose journeys ended somewhere within this patch of Western Atlantic, leaving behind questions that have, over the decades, accumulated like sediment on the ocean floor. These are the cases that gave the Bermuda Triangle its reputation, and they deserve to be told plainly, without embellishment, because the facts themselves are quite sufficient, and because there is something respectful in simply stating what is known and acknowledging what is not. We might begin with a ship called the USS Cyclops, a naval collier of considerable size, measuring some 542 feet in length and displacing nearly 20,000 tons when fully laden. She was, in the parlance of her era, a Proteus-class collier, built to carry coal and other bulk cargo for the United States Navy, and she had served reliably through the early years of the First World War, transporting fuel to American warships stationed across the Atlantic. In March of 1918, the Cyclops departed from Rio de Janeiro bound for Baltimore, carrying a cargo of manganese ore, that dense metallite mineral used in steelmaking. Some 11,000 tons of it settled deep in her holds. She carried also 542 souls, a complement of crew and passengers that included naval personnel and a number of civilians, and she stopped briefly in Barbados to take on additional supplies before continuing northward along her planned route. She was never seen again. No wreckage was found. No distress signal was received, and no survivor ever emerged to tell what happened in those waters between the Caribbean and the American coast. The loss of the Cyclops remains, to this day, the largest non-combat loss of life in the history of the United States Navy, a distinction that lends the disappearance a certain weight in the historical record, quite apart from any associations with the Bermuda Triangle, which had not yet acquired its name or its mythology in 1918. At the time, speculation centered on German submarines, on structural failure, on the possibility that her heavy cargo had shifted in rough seas and caused her to capsize, or on the behavior of her captain, a man named George Worley, whose background and temperament had drawn some concern from his superiors. None of these theories has ever been confirmed, and the Cyclops remains where she sank, presumably somewhere beneath the Atlantic, her exact location still unknown more than a century later. 45 years would pass before another vessel would enter the catalogue with comparable notoriety, and this was the Marine Sulphur Queen, a tanker of rather unusual character that had been converted from her original purpose to carry a cargo few ships were designed to transport. She had begun her working life as a T2 tanker, one of those standardized vessels built in great numbers during the Second World War to move petroleum products across the oceans. And in the late 1950s, she was retrofitted with insulated tanks and heating equipment to carry molten sulfur, that pale yellow element that must be kept liquid at temperatures above 240 degrees Fahrenheit, lest it solidify into an unworkable mass. In February of 1963, the Marine Sulphur Queen departed from Beaumont, Texas, bound for Norfolk, Virginia, with 39 crew members aboard and approximately 15,000 tons of molten sulfur sloshing gently in her heated tanks. She passed through the Straits of Florida, sent a routine radio message indicating her position, and then, like the Cyclops before her, simply ceased to exist as far as the world was concerned. A search was mounted, of course, and some debris was eventually recovered, including life jackets, a life ring, and fragments of material that suggested the ship had met with some catastrophic event. But the Marine Sulphur Queen herself was never found, and the precise nature of her end remains a matter of speculation informed by what investigators knew of her condition. She had been, by several accounts, a vessel showing her age, with a hull that had developed cracks and a structure that had been significantly modified from its original design. And the Coast Guard's subsequent investigation raised serious questions about whether she should have been carrying such a hazardous cargo at all. The possibility of an explosion, given the volatile nature of sulfur and the presence of heating equipment, was considered likely, as was the chance that structural failure had simply opened her hull to the sea. What is notable, from our present vantage, is that the loss of the Marine Sulphur Queen, while tragic, was explicable in terms that required no mystery beyond the ordinary mysteries of seafaring, the unseen moment when metal gives way and the ocean claims what it will pull. The aircraft that disappeared in this region tend to occupy a different space in the public imagination, perhaps because flight itself seems more precarious than sailing, or perhaps because the absence of wreckage on the ocean surface feels more absolute when it is an aeroplane that has gone down rather than a ship. Among the most discussed of these aerial disappearances are two aircraft operated by British South American Airways, a carrier that existed for only a few years in the late 1940s before being absorbed into the British Overseas Airways Corporation. The first was the Star Tiger, a four-engined Avro Tudor Fourth that departed from Santa Maria in the Azores on the 28th of January 1948, bound for Bermuda with a complement of 25 passengers and 6 crew. The flight had already been delayed by headwinds and mechanical difficulties, and the aircraft was flying lower than usual to avoid the worst of the weather. which meant that her fuel reserves were being consumed more rapidly than planned. Her last radio transmission indicated that she expected to arrive in Bermuda on schedule, and then she was heard from no more. The search that followed found nothing. Not a fragment of wreckage, not a body, not an oil slick. And the official inquiry concluded that the cause of the loss could not be determined with certainty. Almost exactly 1 year later, on the 17th of January 1949, a sister aircraft named Star Ariel departed from Bermuda bound for Kingston, Jamaica, and she too vanished without sending any distress signal or leaving any trace. She had taken off in fair weather. Her captain had reported reaching cruising altitude and switching radio frequencies. And then there was silence. The investigation into her loss was similarly inconclusive, though it noted certain concerns about the Tudor Fourth design, including questions about the aircraft's heating system and the possibility of fire or structural failure at altitude. British South American Airways would cease operations not long afterward, and the Tudor Fourth would be withdrawn from passenger service, its reputation irreparably damaged by these losses and by a general sense that the aircraft had been rushed into service before its problems had been fully resolved. What we might say, looking back, is that these disappearances occurred during a period when aviation was still maturing as a technology, when aircraft systems were less redundant and less well understood, and when the overwater routes of the Atlantic presented challenges that could overwhelm even experienced crews. There was also a Douglas DC-3, one of those twin-engined workhorses that had revolutionized commercial aviation in the 1930s and remained in widespread use for decades afterwards. This particular aircraft, bearing the registration NC-1682, departed from San Juan, Puerto Rico, on the evening of the 28th of December 1948, bound for Miami with 32 passengers and crew aboard. The flight was operated by Airborne Transport, and it was, by the standards of the day, a routine journey across the Caribbean waters to the Florida coast. The captain radioed to approach control when he was some 50 miles south of Miami, reporting that he could see the city lights and expected to arrive shortly, and then the aircraft was neither seen nor heard from again. The search found no wreckage, and the disappearance was never explained, though various theories have been offered over the years, including fuel exhaustion due to improper flight planning, electrical failure that disabled the radio and navigation equipment, or a controlled descent into water that left the aircraft largely intact and therefore difficult to locate from the air. Not all the disappearances in this region involved large vessels or commercial aircraft. Some were smaller, more intimate, the sort of losses that might pass unnoticed in the wider world, but which carry their own weight for those who remember. One such case involved a pleasure craft named Witchcraft, a 23-foot cabin cruiser owned by a Miami businessman named Dan Burak, who took her out on the evening of the 22nd of December 1967 to view the holiday lights along the Miami shoreline. He was accompanied by a friend, a Catholic priest named Patrick Horgan, and the two men motored out to a buoy about 1 mile from the harbor entrance, where they intended to enjoy the festive display from the water. At some point during the evening, Burak radioed the Coast Guard to report that his vessel had struck something and that he needed a tow. though he emphasized that there was no immediate danger and that the boat was in no distress. A Coast Guard cutter arrived at the reported position within 19 minutes, but found nothing. No witchcraft, no Burak, no Father Horgan, and no evidence of what might have happened in that brief interval. The search continued for days and covered thousands of square miles, but neither the boat nor the men were ever found. These cases, and others like them, have accumulated over the years to form the foundation of the Bermuda Triangle legend, each disappearance adding another entry to the ledger of the lost Ost, each unanswered question inviting speculation and, eventually, mythology. And yet, it is worth noting, as we settle into this accounting, that those institutions whose business it is to assess maritime risk have not found the Bermuda Triangle to be statistically unusual. Lloyd's of London, that venerable insurance market that has been underwriting ships and their cargoes since the late 17th century, has examined the loss records for this region and concluded that the rate of incidence is not significantly higher than in other comparable areas of the ocean. The underwriters at Lloyd's, who have every financial incentive to identify dangerous waters and adjust their premiums accordingly, do not charge more to insure vessels transiting the Bermuda Triangle than they do for vessels crossing other busy shipping lanes. This is a rather telling detail, because insurance markets are not given to sentimentality or speculation. They are interested only in probability and loss, and if the Bermuda Triangle were truly more hazardous than other waters, the actuarial tables would reflect this. The United States Coast Guard, which has responsibility for search and rescue operations throughout this region and therefore has direct experience with the incidents that occur here, has likewise stated that the Bermuda Triangle does not exhibit any unusual characteristics when compared to other heavily trafficked areas of the ocean. The Coast Guard has noted that the region sees a great deal of maritime and aviation traffic, including pleasure craft operated by inexperienced sailors, commercial shipping following the major trade routes, and aircraft crossing between the Americas and Europe, and that this volume of activity inevitably produces a certain number of accidents, equipment failures, and human errors. The weather in this part of the Atlantic can be severe and unpredictable, with sudden storms and waterspouts common during certain seasons. And the Gulf Stream, that great river of warm water flowing northward along the coast, can rapidly disperse wreckage and make the recovery of evidence difficult. In other words, the Coast Guard's position is that the losses attributed to the Bermuda Triangle are explicable by ordinary causes, and that the apparent mystery is largely a function of selective attention and narrative embellishment, rather than any genuine anomaly in the underlying data. This is perhaps the most restful observation we can make about the ledger of the lost, that the entries it contains, while tragic and in some cases genuinely puzzling, do not require us to posit anything beyond the ordinary hazards of travel across water and through air. Ships have always sunk, aircraft have always crashed, and the sea has always been reluctant to surrender its secrets. The Bermuda Triangle, for all its reputation, is simply a portion of that larger ocean where these truths apply as they do everywhere else, and where the accumulation of stories has created an impression of mystery that the statistics do not support. This does not diminish the sorrow of the losses themselves, or the genuine uncertainty that surrounds some of the individual cases. But it does suggest that the ledger, while long, is not evidence of anything more than the fundamental unpredictability of human journeys across the deep. Beneath the waves of the Bermuda Triangle lies a world of remarkable geological complexity, a landscape as varied and dramatic as any found on the continents above, yet hidden from our everyday view by thousands of feet of dark Atlantic water. As you settle in and allow your breathing to slow, we might turn our attention downward now, away from the ships and aircraft that have captured so much imagination, and instead consider the ancient stone and sediment that forms the foundation of this region. The deep trenches and plateaus that have been shaped over millions of years by the patient work of tectonic forces and oceanic currents. The seafloor beneath the triangle is not, as one might casually assume, a simple flat expanse of sand and silt stretching uniformly from the Americas toward Europe and Africa. Rather, it presents a complex arrangement of trenches, ridges, plateaus, and basins, each with its own geological history, and each contributing in subtle ways to the conditions experienced by vessels passing overhead. Researchers from institutions such as the Woods Hole Oceanographic Institution, located on Cape Cod in Massachusetts, have spent decades mapping and studying this intricate underwater terrain, using sonar systems and submersible vehicles to build an increasingly detailed picture of what lies in the perpetual darkness below. Perhaps the most striking feature of the region is the Puerto Rico Trench, which marks the boundary where the North American tectonic plate meets the Caribbean plate in a zone of active geological interaction. This trench represents the deepest point anywhere in the Atlantic Ocean, plunging to a maximum depth of approximately 27,493 feet below the surface of the sea. To place this measurement in a context that the mind can more easily grasp, we might note that this depth exceeds the height of Mount Everest above sea level by several thousand feet, meaning that if one were somehow able to place the tallest mountain on Earth into the Puerto Rico Trench, its summit would still remain submerged beneath more than a mile of water, lost in the cold and the dark. The trench stretches for approximately 500 miles along the northern boundary of Puerto Rico and the Virgin Islands, a vast chasm in the Earth's crust that continues to deepen incrementally as the tectonic plates grind against one another in their endless slow motion. The water at these depths is compressed by the immense weight of the column above it, and the pressure reaches values that would crush most human-made structures into fragments. Very little light penetrates beyond the first few hundred feet of ocean, and so the floor of the trench exists in a state of permanent night, inhabited by creatures specially adapted to conditions that would be instantly fatal to surface-dwelling life. Moving westward from the Puerto Rico Trench toward the continental shelf of North America, the seafloor rises gradually through a series of terraces and plateaus, among which the Blake Plateau occupies a particularly interesting position. This relatively flat region extends roughly from the coast of Florida northward toward the Carolinas, lying at depths between approximately 2,000 and 3,000 feet below sea level. The Blake Plateau is notable for its unusual geological composition, featuring extensive formations of limestone that were deposited over millions of years when this area lay in shallower, warmer waters that supported the growth of coral and other calcium-secreting organisms. These underwater limestone formations create a distinctive terrain of ridges and depressions, with areas where ancient reef structures have been preserved beneath layers of more recent sediment. The limestone is porous in places, riddled with cavities and channels that were carved by water during periods when sea levels were lower and portions of the plateau may have been exposed to air. Scientists studying the Blake Plateau have documented a remarkable variety of geological features, including steep escarpments where the plateau edge drops away toward deeper water, and regions where the limestone has been sculpted into elaborate patterns by the steady action of deep currents. The currents that flow across and around the Blake Plateau are themselves worthy of contemplation as you lie there quietly in the darkness. The Gulf Stream, that great river of warm water that flows northward along the eastern seaboard of the United States, passes directly over portions of the plateau, carrying roughly 30 million cubic meters of water every second at velocities that can exceed 4 knots in certain locations. This current does not flow in a simple straight line, but rather meanders and shifts, sometimes developing large loops and eddies that can persist for weeks or months before dissipating. Where the Gulf Stream interacts with the complex topography of the seafloor, it can create upwellings and downwellings, areas where water rises from the depths or sinks from the surface, producing conditions at the sea surface that can change rapidly and unpredictably. Deeper still, beneath the relatively swift waters of the Gulf Stream, other currents move more slowly in different directions, carrying cold, dense water that has sunk in the polar regions and is making its gradual journey toward the equator. These deep currents are influenced by the shape of the seafloor in ways that scientists are still working to understand fully, channeled through gaps in underwater ridges and accelerated where they pass over obstacles. The interaction between surface currents, deep currents, and the irregular bathymetry of the region creates a three-dimensional circulation pattern of considerable complexity, one that can occasionally produce unexpected conditions at the surface where ships and sailors must navigate. Among the more intriguing discoveries made by scientists studying the seafloor beneath the Bermuda Triangle region are the extensive deposits of methane hydrate that lie buried in the sediments along the continental shelf and slope. Methane hydrate is a curious substance, a form of ice in which molecules of methane gas are trapped within a crystalline lattice of frozen water. It forms only under specific conditions of high pressure and low temperature, conditions that are commonly found in ocean sediments at depths below about 500 meters. The United States Geological Survey has conducted numerous studies of methane hydrate deposits along the Atlantic margin, documenting massive concentrations of this material in sediments that have accumulated over millions of years. The methane contained in these deposits originated from the decomposition of organic matter, the remains of countless microscopic organisms that drifted down through the water column and accumulated on the seafloor, where bacteria slowly converted their carbon into methane gas. Under the right conditions, this gas became locked into the hydrate form, stabilized by the cold temperatures and crushing pressures of the deep ocean. The deposits along the continental shelf east of the United States are estimated to contain enormous quantities of methane, enough that they have attracted interest both as a potential energy resource and as a possible factor in past climate changes. What makes methane hydrate particularly relevant to our quiet contemplation is its potential to destabilize suddenly under certain conditions, releasing large quantities of gas into the water column in events that geologists call blowouts or eruptions. Such events are believed to have occurred many times throughout geological history, triggered by changes in temperature, pressure, or the mechanical stability of the sediments in which the hydrate was buried. In 1981, researchers studying the floor of the North Sea discovered extensive fields of craters and pockmarks that provided compelling evidence of ancient methane blowouts. Places where massive quantities of gas had erupted from the seabed in events that may have lasted only minutes but left permanent scars on the underwater landscape. The question of whether such methane releases might pose a hazard to ships has been the subject of scientific investigation, including laboratory experiments conducted by researchers seeking to understand the physics of what happens when large quantities of gas bubbles rise through water. Dr. Bruce Donato, a physicist who has studied this phenomenon, conducted experiments demonstrating that when sufficient quantities of bubbles are introduced into water, they can reduce the effective density of the water to the point where objects that would normally float become unable to support themselves and sink. The bubbles, being composed of gas rather than liquid, provide much less buoyancy than the water they displace, and a ship caught in a region of heavily aerated water might suddenly find itself unable to stay afloat. Whether such events have actually occurred in the Bermuda Triangle region remains a matter of scientific uncertainty, as the conditions required to produce a methane blowout of sufficient magnitude to endanger a ship are quite specific, and such events would leave little direct evidence on the surface. The hydrate deposits do exist, as documented by USGS surveys and other research programs, and the geological record shows that blowouts have occurred in other parts of the world, but proving that any particular ship was lost to this mechanism would require evidence that is exceedingly difficult to obtain from the deep ocean floor. Farther out into the Atlantic, beyond the continental shelf and the Blake Plateau, the geology of the seafloor is dominated by the influence of the Mid-Atlantic Ridge, that vast underwater mountain chain that runs down the center of the ocean basin like a seam on a baseball. The ridge marks the boundary where the American plates are pulling away from the European and African plates, with new oceanic crust being created continuously as magma rises from the Earth's mantle to fill the gap. This process of seafloor spreading has been ongoing for approximately 180 million years, gradually widening the Atlantic Ocean at a rate of roughly 2.5 centimeters per year, about the speed at which human fingernails grow. The ridge itself lies mostly at depths between 2,000 and 3,000 meters, though it rises above sea level in a few locations, most notably in Iceland. Along its flanks are scattered remnants of underwater volcanic activity, ancient seamounts and volcanic cones that were formed over hotspots in the mantle and then carried slowly away from their source by the conveyor belt of spreading seafloor. Some of these volcanic remnants rise thousands of feet above the surrounding abyssal plain, creating obstacles and irregularities in the deep circulation of the ocean. The researchers at Woods Hole Oceanographic Institution and other marine science centers have devoted considerable effort to understanding the complex bathymetry of the Western Atlantic, the detailed shape and composition of the seafloor that influences everything from current patterns to the distribution of marine life. Using multi-beam sonar systems that can map wide swaths of ocean floor with each pass of a research vessel. They have built up detailed charts showing the ridges and valleys, the canyons cut by ancient rivers during ice ages when sea levels were lower, the fields of sediment, drifts shaped by deep currents into wave-like formations that can stretch for miles. This bathymetry affects the surface conditions that sailors experience in ways that are not always intuitive. Where deep currents are forced to flow over or around underwater obstacles, they can create internal waves, oscillations in the density layers of the ocean that propagate through the water, much like waves on the surface, but at much larger scales. These internal waves can reach heights of hundreds of feet and travel for great distances before dissipating. And when they encounter the continental shelf or other shallow areas, they can break, releasing their energy in ways that create unpredictable surface turbulence. As you rest there with your eyes closed, breathing slowly and evenly, you might picture this hidden landscape beneath the waves. The plunging trench, deeper than any mountain, is tall. The limestone plateaus with their ancient coral formations, the vast deposits of methane ice waiting in the cold sediments, the volcanic remnants and spreading ridges that mark the slow rearrangement of continents. It is a world that operates on timescales far longer than human lives or human memory, where the forces that shape the land are patient and inexorable, where the darkness at the bottom of the sea holds secrets that we are only beginning to understand through the careful application of science and technology. The geology beneath the Bermuda Triangle is remarkable not because it is anomalous or mysterious, but because it represents such a varied and active sample of the processes that shape our planet. Processes that continue today, just as they have for millions of years before any human set sail across these waters, and will continue for millions of years after the last ship has passed. And now we turn our attention to a rather lovely aspect of navigation that has long captured the imagination of those who wonder about the Bermuda Triangle, and that is the behavior of compasses in this particular stretch of ocean, and the gentle wandering of magnetic north as it traces its quiet path across the centuries. To understand why compasses have been a subject of curiosity in these waters, we must first become comfortable with a concept called magnetic declination, which sounds rather more complicated than it actually is, and which describes something quite natural about the way our planet works. You see, when we speak of north, we are actually speaking of two different norths. And this is where things become gently interesting in the way that geography and physics so often do when they overlap. The first north is true north, which is also called geographic north, and this is the point at the very top of our planet where the Earth's axis of rotation meets the surface, that fixed point around which our world spins each day as it has done for billions of years. The second north is magnetic north, and this is something altogether different, for it is the point toward which a compass needle is drawn by the Earth's magnetic field. And this point is not fixed at all, but rather wanders about the Arctic region like a slow and contemplative traveler with no particular schedule to keep. The difference between these two norths, measured as an angle from wherever you happen to be standing or sailing, is what we call magnetic declination, and it varies depending on where you are on the Earth's surface. In some places, magnetic north lies to the east of true north, and we call this easterly declination. And in other places, magnetic north lies to the west of true north. And we call this westerly declination. And there are yet other places where the two norths align perfectly, where a compass pointing to magnetic north is also pointing to true north. And these special locations are said to lie along what is called the agonic line. The word agonic comes from the Greek, meaning without angle, which is a rather pleasant way of describing a place where the angle of declination is zero. Now, here is where our story touches upon the Bermuda Triangle in a way that has contributed to its reputation over the years. For quite some time, the Bermuda Triangle region was one of only two places on Earth where this agonic line passed through, where compasses pointed to both magnetic and true north simultaneously. The other place was far away on the opposite side of the Pacific Ocean, near Japan, in a region sometimes called the Devil's Sea or the Dragon's Triangle, which has its own collection of maritime stories, though these need not concern us this evening. This coincidence, that both the Bermuda Triangle and the Devil's Sea happen to lie along the agonic line, was noted by various writers and researchers over the years, and some suggested that perhaps this magnetic peculiarity might explain the strange occurrences reported in both regions. It was an appealing idea in its way, for it seemed to offer a natural explanation, something rooted in the physical properties of the Earth itself rather than in the supernatural. However, and this is important to understand as we settle deeper into our pillows, the agonic line does not stay in one place. It moves, and it has been moving westward across the Earth's surface for centuries, drifting slowly like a great invisible ribbon being pulled by forces deep within our planet. In the year 1492, when Christopher Columbus sailed through these waters on his first voyage to the Americas, the agonic line did indeed pass through what we now call the Bermuda Triangle. And Columbus, being a careful observer, as all good navigators must be, noticed something curious about his compasses during this journey. He recorded in his log that the compass needles shifted slightly, and this observation has been cited many times over the centuries as early evidence of unusual magnetic behavior in these waters. But when we place Columbus's observations in their proper context, with what we now know about magnetic declination and the position of the agonic line at that time, his notes become rather less mysterious. What Columbus was observing was simply the natural variation of magnetic declination, the gentle transition from one declination zone to another as his ships crossed the agonic line. Any experienced navigator of that era would have been familiar with the fact that compass behavior changes as one travels across the ocean, though the precise mechanisms were not yet fully understood. Today, the agonic line has moved considerably westward, and it no longer passes through the Bermuda Triangle at all, but rather runs down through the central United States, passing somewhere around Louisiana and continuing southward through the Gulf of Mexico. The magnetic declination in the Bermuda Triangle today is approximately 15 degrees westerly, which means that a compass needle in those waters points about 15 degrees to the west of true north. This is not unusual at all, and it is simply what one finds at this longitude, and modern navigators account for it automatically in their calculations, just as they account for declination everywhere else on Earth. The movement of the agonic line is part of a much larger pattern of change in the Earth's magnetic field, and understanding this field helps us appreciate why compasses behave as they do. Deep within our planet, in the outer core, some 2,900 kilometers beneath the surface, there flows a vast ocean of liquid iron and nickel, heated by the decay of radioactive elements and by the slow cooling of the inner core. This molten metal moves in great convective currents, rising and falling and circulating in patterns influenced by the Earth's rotation. And as it moves, it generates electrical currents. And these electrical currents, in turn, generate magnetic fields. This is the geodynamo, as scientists call it, and it is the source of the magnetic field that surrounds our planet and shields us from the solar wind. But the geodynamo is not a simple or static thing, for the patterns of flow in the outer core are complex and ever-changing. And so, the magnetic field they produce is also complex and ever-changing. The magnetic poles wander, the strength of the field fluctuates, and the patterns of declination shift across the Earth's surface over timescales of decades and centuries. This is entirely normal behavior for a planet like ours, and it has been going on for billions of years. Not far from the Bermuda Triangle, in the South Atlantic Ocean off the coast of Brazil, there exists a region called the South Atlantic Anomaly, which is an area where the Earth's magnetic field is weaker than it is elsewhere. This anomaly is of interest to scientists and to space agencies because it allows more cosmic radiation to penetrate closer to the Earth's surface, which can affect satellites and spacecraft passing through it. The South Atlantic Anomaly is caused by the tilt between the Earth's rotational axis and its magnetic axis, combined with peculiarities in the flow of the outer core beneath that region. Some writers have tried to connect the South Atlantic Anomaly to the Bermuda Triangle, suggesting that perhaps magnetic irregularities extend northward into the triangle's waters. But the South Atlantic Anomaly is centered thousands of kilometers to the south, over Brazil and the South Atlantic, and while its edges do extend somewhat, careful measurements have shown no unusual magnetic behavior in the Bermuda Triangle itself. And this brings us to the important work of scientists who have actually gone out and measured the magnetic field in these waters, rather than simply speculating about what might be found there. The National Oceanic and Atmospheric Administration, which we often call NOAA, conducts regular surveys of the Earth's magnetic field as part of its mission to understand our planet and to provide accurate data for navigation, working in conjunction with the National Geophysical Data Center, which maintains vast archives of geophysical measurements. NOAA scientists have mapped the magnetic field across the Bermuda Triangle region with great precision. They use magnetometers, which are instruments that measure the strength and direction of magnetic fields. And they deploy these instruments on ships, on aircraft, and on fixed observatories. The data they have collected over decades tells a consistent story, which is that the Bermuda Triangle exhibits no unusual magnetic anomalies. The magnetic field there is exactly what one would expect for that latitude and longitude, varying smoothly across the region in accordance with the global patterns produced by the geodynamo. There are no sudden jumps, no inexplicable dead zones, no compass-disrupting irregularities of the sort that have sometimes been proposed in popular accounts. One particularly thorough investigation was conducted in 1970 by an expedition sponsored by National Geographic, which set out specifically to test the hypothesis that unusual magnetic conditions might explain the disappearances attributed to the Bermuda Triangle. The expedition covered a wide area, taking careful measurements at many locations, and their conclusion was unambiguous. They found nothing out of the ordinary, nothing that would cause a compass to behave any differently there than it would behave at any other location with similar declination values. The magnetic field was as gentle and predictable as anywhere else on the ocean. Now, it is worth taking a moment to appreciate how important compass accuracy was to navigation in the centuries before modern technology. For this helps us understand why magnetic declination mattered so much to sailors of earlier eras. Before the advent of radio navigation systems, before radar and satellite positioning, the compass was one of the few reliable tools a sailor had for maintaining a sense of direction in the open ocean. A skilled navigator would use the compass in conjunction with celestial observations, timing the positions of the sun and stars with a sextant to determine latitude and, with more difficulty, longitude. But between celestial sightings, which could only be taken when the sky was clear and the horizon visible, the compass was the primary guide. And so, any uncertainty about compass behavior was a serious matter. Navigators had to know the declination for the waters they were sailing, and they had to apply corrections to convert magnetic headings into true headings. If they miscalculated, or if they were unaware that declination varied from place to place, they could end up far from where they intended to be. Over long voyages, small errors in heading could accumulate into significant deviations from the intended course. This is why Columbus's observations about compass variation were noteworthy in his time, and why early cartographers began including declination information on their charts as understanding of the phenomenon grew. Navigation was a difficult art, requiring skill and knowledge and constant attention, and the sea was unforgiving of mistakes. But here is the thing that removes much of the mystery from compass-related explanations for Bermuda Triangle incidents. Modern navigation no longer relies primarily on magnetic compasses. Since the 1990s, the Global Positioning System, which we call GPS, has become the dominant method of determining position and heading at sea. GPS works by receiving signals from a constellation of satellites orbiting the Earth, and by calculating the precise distance to multiple satellites simultaneously. A GPS receiver can determine its position with remarkable accuracy, often within a few meters. This technology is entirely independent of magnetic fields. It does not care about declination or anomalies, and it works continuously, day and night, in any weather, at any location on the planet's surface. Ships and aircraft today navigate primarily by GPS, and while they may still carry magnetic compasses as backup instruments, these are no longer the critical tools they once were. Any concerns about compass behavior in the Bermuda Triangle, whatever their validity might have been in earlier decades, have become largely irrelevant in the modern era of satellite navigation. A ship crossing the Bermuda Triangle today knows its exact position at all times, displayed on electronic charts with precision that would have seemed miraculous to Columbus or to any navigator of the pre-electronic age. And so, we find ourselves at a gentle resolution to the question of wandering compasses in these storied waters. The magnetic declination in the Bermuda Triangle is real. as it is everywhere on Earth, and it has changed over the centuries as the agonic line has drifted westward. But there is nothing unusual or mysterious about the magnetic field in this region. Nothing that would cause compasses to fail or to give wildly incorrect readings. The investigations have been done, the measurements have been taken, and the conclusion is a reassuring one. The Earth's magnetic field in the Bermuda Triangle is simply part of the great flowing pattern of magnetism that wraps around our planet, generated by the slow churning of molten iron in the depths below, changing gradually over time in ways that scientists understand and can predict. And with this knowledge settling gently around us like a comfortable blanket, we can let our thoughts drift away from compasses and magnetic poles, knowing that the needle points where it should, that the variations have been mapped, and that the science is clear and calm and entirely undramatic. The weather that moves through the Bermuda Triangle is, in many ways, unlike weather found in most other places on Earth, not because it follows different physical laws, but because it arises from a particular confluence of conditions that exist here and almost nowhere else with quite the same intensity. The meeting of warm and cool waters, the proximity of tropical and temperate air masses, the vast fetch of open ocean, and the interplay of high-pressure systems all combine to create an environment where storms can form with remarkable speed, where clear skies can turn opaque in minutes, and where the sea itself can reshape into forms that seem, to those unfamiliar with the physics involved, almost impossible. Understanding these phenomena requires no recourse to mystery, only a patient attention to the mechanics of air and water and the energy that flows between them. And so we shall take our time now to consider each of these meteorological events in turn, moving slowly through the science as one might move through a calm sea, noting each detail as it passes beneath our consideration. Among the most sudden and violent atmospheric events that occur in this region are microbursts, which are intense downdrafts of air that descend from the base of a thunderstorm and strike the surface of the ocean or land with tremendous force before spreading outward in all directions. A microburst typically develops when rain falls through dry air beneath a storm cloud, causing rapid evaporation that cools the air dramatically. And this cooled air becomes denser than the surrounding atmosphere and begins to sink with increasing velocity. By the time this column of descending air reaches the surface, it may be traveling at speeds exceeding 100 miles per hour, and when it strikes the water or ground, it fans out horizontally, creating winds that can match or exceed those of a hurricane, albeit in a much more localized area. The entire event may last only 5 to 15 minutes, which is part of what makes microbursts so difficult to predict and so dangerous to encounter, particularly for aircraft on approach to landing or for small vessels that may have no warning before the wind suddenly arrives. In the warm, humid atmosphere of the Bermuda Triangle, where towering cumulonimbus clouds can develop with remarkable speed during the afternoon hours, the conditions for microburst formation are often present, and pilots and mariners operating in these waters have learned to treat building thunderheads with considerable respect, understanding that the violence they contain may be delivered to the surface with almost no advance notice. Waterspouts represent another atmospheric phenomenon that occurs in the Bermuda Triangle with a frequency unmatched anywhere else on the planet, and the Florida Straits in particular see between 400 and 500 of these rotating columns of air and water spray each year, making this narrow passage between Florida and the Bahamas the most active waterspout region in the world. A waterspout is essentially a tornado that forms over water. Though most waterspouts are of the fair weather variety and develop beneath cumulus clouds that show little sign of the severe weather typically associated with tornadoes on land. These fair weather waterspouts form when surface heating creates instability in the lower atmosphere, and light winds at different heights cause a gentle horizontal rotation in the air, which can then be tilted vertically and intensified as warm, moist air rises rapidly from the sea surface. The resulting funnel may extend from cloud base to water surface, drawing up a spray of seawater that makes the lower portion visible. And while most waterspouts have wind speeds between 40 and 70 miles per hour, some can reach intensities comparable to a weak tornado, posing genuine hazards to small boats and low-flying aircraft. The waters of the Florida Straits are particularly conducive to waterspout formation because they are warm throughout much of the year, surrounded by land masses that influence local wind patterns, and subject to afternoon heating that triggers the convective processes necessary for these rotating columns to develop. On some days, particularly during the late summer months, multiple waterspouts can be visible simultaneously from the deck of a ship crossing these waters, their pale funnels descending from flat-bottomed clouds and wandering slowly across the sea surface before dissipating as quickly as they appeared. The phenomenon, known as electronic fog, has been the subject of research by Dr. David Pares, a professor at the University of Nebraska, who has proposed that certain electromagnetic anomalies in the atmosphere may, under specific conditions, create disorienting effects on aircraft instruments and human perception. Dr. Pares has suggested that variations in electromagnetic fields, possibly related to the interaction of solar radiation with the Earth's magnetic field or to the presence of unusual atmospheric conditions, could generate localized phenomena that affect compass readings, radio communications, and visual perception. While this research remains outside the mainstream of meteorological science and has not been widely replicated or accepted by the broader scientific community, it represents an attempt to understand reports from pilots and mariners who have described entering areas of fog or haze in which their instruments behaved erratically and their sense of time and space seemed altered. Whether such electronic fog phenomena have any basis in measurable physical effects remains an open question, and most atmospheric scientists attribute reports of instrument malfunction and disorientation to more conventional causes, including magnetic variation, equipment failure, and the psychological effects of reduced visibility. Nevertheless, the continuing investigation of these claims reminds us that the atmosphere is a complex medium, influenced by electromagnetic radiation, charged particles, temperature gradients, and pressure differentials in ways that we may not yet fully understand, and that scientific humility requires us to remain open to explanations that have not yet been thoroughly tested. The Gulf Stream, that great river of warm water flowing northward through the Straits of Florida and along the eastern coast of North America, plays a crucial role in creating the sudden weather changes for which the Bermuda Triangle is known, and its influence on local meteorology cannot be overstated. The Gulf Stream carries water with a temperature that is typically 15 to 20 degrees Fahrenheit warmer than the surrounding ocean. And this temperature differential creates a boundary zone where atmospheric conditions can change dramatically over very short distances. When cooler air moves across the surface of the Gulf Stream, the warm water heats it from below, causing rapid evaporation and the formation of fog, low clouds, and convective activity that can develop into thunderstorms. Conversely, when warm, moist air moves from the Gulf Stream over cooler coastal waters, advection fog can form with remarkable speed, reducing visibility from many miles to less than a few hundred feet in a matter of minutes. This capacity for rapid fog formation is well known to mariners operating in these waters, who may depart from port under clear skies only to find themselves enveloped in dense fog as they cross the temperature boundary marking the edge of the Gulf Stream. The energy exchange between ocean and atmosphere in this region is immense, and the weather systems that develop here can grow and intensify with a speed that reflects the abundant supply of heat and moisture available to fuel them. Understanding the Gulf Stream's role in regional meteorology helps explain why the weather in the Bermuda Triangle can seem so unpredictable to those who are not familiar with the physics of air-sea interaction, and why forecasting conditions in this area remains challenging even with modern technology. Rogue waves, those towering walls of water that seem to appear from nowhere and overwhelm vessels that were navigating seas that appeared manageable only moments before, represent another hazard of the Bermuda Triangle that was for many years dismissed as mariners' exaggeration, but is now recognized as a real and measurable phenomenon. The Queen Elizabeth II, one of the great ocean liners of the 20th century, encountered a rogue wave in the North Atlantic in September of 1995 that was estimated to be approximately 95 feet in height. A wall of water that towered over the bow of the ship and broke across the forward decks with tremendous force. The captain described the experience as watching the ship sail toward the white cliffs of Dover, and the wave was so large that it briefly obscured the sky. This encounter, along with subsequent satellite measurements and wave buoy data, has confirmed that waves exceeding 100 feet in height do occur in the open ocean, though they are rare and difficult to predict. NOAA satellites equipped with radar altimeters have documented the existence of these extreme waves, which appear to form when multiple wave trains traveling in different directions intersect and combine their energies, creating a single wave that can be twice or even 3 times the height of the surrounding seas. In the Bermuda Triangle, where the Gulf Stream creates strong currents that can interact with wind-driven waves to create steep, confused seas, the conditions for rogue wave formation may be present more frequently than in calmer ocean regions, and the historical record of ships that have disappeared without trace in these waters must be considered in light of this now documented phenomenon. The Bermuda Azores High, a semi-permanent subtropical high-pressure system that sits over the central Atlantic Ocean, exerts a powerful influence on weather patterns throughout the Bermuda Triangle and contributes to the unpredictability that characterizes the region. During the summer months, this high-pressure system typically strengthens and shifts northward, bringing warm, stable conditions to much of the western Atlantic. But the position of the high is never fixed. and its movements can create dramatic changes in local weather. When the high-pressure system weakens or shifts, it can allow tropical disturbances to move northward into the Bermuda Triangle, bringing heavy rain, strong winds, and rough seas to areas that were experiencing calm conditions only days before. The clockwise rotation of winds around the high-pressure system also influences the direction and speed of the Gulf Stream, which in turn affects the temperature gradients and weather patterns described earlier. The interplay between the Bermuda Azores High and other atmospheric features, including cold fronts moving eastward from North America and tropical waves moving westward from Africa, creates a dynamic environment where weather conditions can change rapidly and where the same location may experience dramatically different conditions from one week to the next. Clear air turbulence, the invisible enemy of smooth flight, occurs in the Bermuda Triangle with a frequency that has been documented by NOAA research, including a 2004 study that examined turbulence reports and atmospheric data from the region. Clear air turbulence develops when layers of air moving at different speeds create shearing forces that generate chaotic motion, typically at high altitudes near the jet stream or at lower altitudes near temperature boundaries and frontal zones. In the Bermuda Triangle, the strong temperature gradients associated with the Gulf Stream and the frequent passage of frontal systems create conditions favorable for clear air turbulence at both high and low altitudes. And aircraft operating in the region may encounter sudden and severe turbulence in areas where no clouds or other visible weather features would provide warning. This invisible turbulence has been implicated in accidents and incidents involving both commercial and private aircraft. And modern flight operations over the Bermuda Triangle include careful attention to pilot reports and atmospheric models that attempt to predict where turbulence is most likely to occur. All of these meteorological phenomena, from microbursts to waterspouts to rogue waves to clear air turbulence, are products of the physical processes that govern the atmosphere and ocean, processes that obey the laws of thermodynamics, fluid dynamics, and electromagnetic radiation. The Bermuda Triangle is not a place where these laws are suspended or altered, but rather a place where the conditions necessary for extreme weather events are present more frequently and more intensely than in many other parts of the world. The meeting of warm and cool waters, the energy of the Gulf Stream, the instability of tropical air masses, and the variability of the Bermuda Azores High all combine to create an environment where nature demonstrates its capacity for sudden and dramatic change. Understanding these phenomena does not diminish their power or their danger, but it does allow us to appreciate that the storms born between sea and sky in this region are expressions of the same physics that governs weather everywhere on Earth, simply operating at a higher intensity and with greater variability than many sailors and pilots are prepared to encounter. And so we come now to consider how this particular patch of ocean, this expanse of water that had always been there, waiting quietly beneath the sun and the stars, came to be wrapped in such elaborate stories, and how those stories were carefully stitched together over time, like a quilt made from fragments of half-remembered news clippings and the natural human longing for mystery in an increasingly mapped and measured world. For many centuries, the waters between Florida, Bermuda, and Puerto Rico were simply waters, and sailors who passed through them noted the usual challenges of seafaring: the storms that could rise with little warning, the currents that pulled in unexpected directions, the vastness that made navigation a matter of skill and patience and no small amount of luck. And when ships were lost, as ships have always been lost at sea, the losses were mourned and recorded and attributed to the ordinary perils of ocean travel, which were considerable enough without any need for embellishment. The transformation of these waters into something else, into a place of legend and whispered speculation, did not happen all at once, but rather accumulated gradually, like sediment settling on the ocean floor, layer upon layer, until the thing that had been built bore only a passing resemblance to the substrate of fact beneath it. And this process of myth-making is itself rather interesting to trace, not for its drama, but for what it reveals about how we humans construct narratives from scattered events and incomplete information. The phrase that would eventually capture the public imagination and give shape to an amorphous collection of maritime incidents was first set down in print by a writer named Vincent Gaddis, who, in February of 1964, contributed an article to a publication called Argosy Magazine, which specialized in adventure stories and tales of the unusual. And in that article, Gaddis referred to the region as the Bermuda Triangle, giving it for the first time a name that was geometric and therefore somehow scientific sounding. A name that suggested boundaries and definition, even though no such boundaries existed in any official sense. Gaddis had drawn upon earlier reports of missing aircraft and vessels, weaving them together into a pattern that implied something strange was occurring in this particular part of the Atlantic, something that set it apart from other waters. And though his article was published in a magazine known more for entertainment than rigorous journalism, the phrase he coined proved remarkably durable, spreading outward through popular culture like ripples from a stone dropped in still water, touching other writers who would pick it up and carry it further still. A decade passed, during which the notion of the Bermuda Triangle continued to circulate in various forms, appearing in magazine articles and paperback books and television programs, growing a little larger with each retelling, accumulating additional incidents and increasingly exotic explanations, until in 1974 a book was published that would cement the myth firmly in the public consciousness and demonstrate just how hungry readers were for mysteries that seemed to defy rational explanation. This book was written by Charles Berlitz, a man who came from a family famous for language instruction and who had a talent for presenting peculiar claims in accessible prose. And his work, titled simply The Bermuda Triangle, became an extraordinary commercial success, selling by some estimates over 20 million copies worldwide and remaining on bestseller lists for years. Translated into dozens of languages and read by people on every continent who were drawn to its promise of genuine enigma in an age when so much of the world had been thoroughly explored and documented. Berlitz gathered together accounts of ships and aircraft that had disappeared in the region, presenting them in language that emphasized their mysterious qualities, while often omitting details that might have made them seem more explicable. And he proposed various theories to account for the losses, ranging from unusual magnetic phenomena to time warps to the possible involvement of extraterrestrial beings. And while few scientists took these suggestions seriously, the book's popularity demonstrated that a significant portion of the reading public found such ideas appealing, or at least entertaining enough to spend money on. The success of Berlitz's book invited scrutiny, however, and it was not long before a researcher named Larry Couchet, who worked as a reference librarian at Arizona State University and therefore had both the training and the inclination to trace claims back to their sources, decided to investigate the incidents that Berlitz and other writers had cited as evidence of the triangle's deadly mysteries. And what Couchet found, after considerable effort spent digging through old newspaper archives, weather records, Coast Guard reports, and Lloyd's of London shipping data, formed the basis of his own book, published in 1975 with the pointed title The Bermuda Triangle Mystery, Solved. Couchet's work was less exciting than Berlitz's, as debunkings generally are, but it was far more careful in its handling of evidence, and what it revealed was that many of the incidents attributed to the Bermuda Triangle had been significantly misrepresented, sometimes through carelessness and sometimes, one might suspect, through a desire to make the stories more compelling than the facts would support. Some ships that were said to have vanished without a trace in calm seas had actually been lost during violent storms that earlier accounts had failed to mention. Storms that were documented in weather records available to anyone who cared to look. And the omission of such crucial context transformed ordinary maritime tragedies into inexplicable mysteries, which was convenient for writers seeking to build a case for something supernatural, but was not especially honest. Other vessels that were counted among the triangle's victims had actually disappeared in entirely different parts of the ocean, sometimes hundreds or even thousands of miles away from the region supposedly bounded by Florida, Bermuda, and Puerto Rico. But their stories had been incorporated into the triangle mythology because they were dramatic and because geographical precision was apparently less important than narrative impact to those doing the incorporating. Still, other incidents that appeared in the literature turned out, upon investigation, to be poorly documented or essentially unverifiable, based on second-hand accounts or newspaper stories that contradicted one another in significant details. And in some cases, the ships or aircraft in question could not be confirmed to have existed at all, which rather undermined their value as evidence of anything. Perhaps most telling of all, Couchet discovered that some vessels that had been listed as having vanished mysteriously were in fact later found, their disappearances having been temporary and explicable, their eventual recovery simply not as interesting to writers as their initial loss and therefore not incorporated into the ongoing narrative, which had already moved on to other, newer mysteries by the time the mundane explanations emerged. The picture that emerged from Couchet's research was not of a region haunted by forces unknown to science, but rather of a busy stretch of ocean where many ships and aircraft passed through regularly, where weather could be unpredictable and sometimes severe, where the Gulf Stream created currents that could scatter debris and complicate search efforts, and where, inevitably, some percentage of those vessels would be lost to the same causes that had claimed ships and aircraft everywhere since humans first ventured onto and above the seas. 5 years after Couchet published his findings, the American public television program Nova aired a documentary that conducted its own investigation into the Bermuda Triangle claims, and the program's researchers arrived at conclusions broadly similar to Couchet's, finding that the statistical evidence for unusual numbers of losses in the region simply did not hold up when examined carefully, and that many of the specific incidents cited as evidence of mysterious forces operating in the triangle had mundane explanations or had been distorted in their retelling. The documentary noted that Lloyd's of London, the venerable insurance market that tracked shipping losses around the world with considerable attention to detail because such losses affected their financial calculations, did not consider the Bermuda Triangle to be a particularly dangerous region and did not charge higher premiums for vessels transiting the area, which they certainly would have done if the waters there were claiming ships at unusual rates. Insurance being a business that pays close attention to statistical risk. The United States Coast Guard, which has responsibility for search and rescue operations throughout the region, and therefore has intimate familiarity with the actual patterns of maritime distress, has consistently maintained that the Bermuda Triangle does not have an unusual number of incidents relative to the amount of traffic that passes through it, and that the vast majority of distress calls they receive in those waters are resolved through routine assistance. Vessels running out of fuel or experiencing mechanical difficulties or finding themselves caught in bad weather. Situations that are addressed without mystery and usually without loss of life. Indeed, the Coast Guard receives somewhere in the vicinity of 8,000 distress calls annually from the waters around Florida and the Caribbean and the Western Atlantic, a number that reflects not supernatural danger, but simply the very large volume of recreational boaters, commercial fishing vessels, cargo ships, and private yachts that traverse this popular and heavily trafficked region. And of those thousands of calls, most result in assistance being rendered and the people involved returning safely to shore with nothing more to show for their adventure than a story to tell and perhaps a repair bill to pay. This brings us to consider the workings of the human mind itself, which is in many ways the true origin of the Bermuda Triangle mystery, for our brains are remarkably skilled at finding patterns in the world around us, a talent that served our ancestors well when they needed to recognize the tracks of prey animals or the warning signs of approaching predators, but which can sometimes lead us astray when we apply it to random events that have no actual connection to one another. Psychologists have a term for this tendency to perceive meaningful connections between unrelated things, and they call it apophenia, a word that comes from the Greek and refers to the experience of seeing patterns where none exist. And it is a deeply rooted feature of human cognition. Not a flaw exactly, but rather a side effect of the same mental machinery that allows us to learn from experience and recognize genuine regularities in our environment. When we hear of a ship disappearing in the Bermuda Triangle, and then another ship some months later, and then an aircraft a few years after that, our pattern-seeking minds are inclined to connect these events, to see them as manifestations of some underlying cause that links them together. Even though ships and aircraft are lost in every part of the world's oceans, and the only thing connecting these particular incidents is the name that someone decided to give to the region where they occurred. Closely related to apophenia is another cognitive tendency known as confirmation bias, which describes our inclination to notice and remember information that supports beliefs we already hold, while overlooking or forgetting information that contradicts them. And this tendency plays a significant role in the persistence of mystery narratives once they have taken hold in popular culture. If you believe that the Bermuda Triangle is a place where strange things happen, you will likely take note when you hear of a vessel lost in that region, filing the incident away as further confirmation of what you already suspected. But you may pay less attention when you hear of vessels lost in the North Sea, or the Pacific, or the Gulf of Mexico. And you are unlikely to register consciously the thousands upon thousands of ships and aircraft that pass through the Bermuda Triangle every year without incident. Because safe arrivals are not news and do not fit the pattern you have come to expect. The scientist and science communicator Carl Sagan, who spent much of his career encouraging the public to think carefully about evidence and to distinguish between genuine science and claims that merely had the appearance of science, discussed the Bermuda Triangle in his writings and public appearances as an instructive example of how pseudoscientific ideas can take hold and spread despite the absence of supporting evidence. Sagan noted that the triangle mythology exhibited many of the hallmarks of pseudoscience, including a reliance on anecdotes rather than systematic data, a tendency to ignore or dismiss contradictory evidence, an appeal to exotic explanations when ordinary ones would suffice, and a resistance to the kind of rigorous testing that genuine scientific hypotheses must undergo before they can be accepted as reflecting something true about the world. He observed that the popularity of the Bermuda Triangle legend said something important about human psychology and about the appetite for wonder that exists in all of us. An appetite that is in itself admirable, but which can lead us astray if we do not balance it with critical thinking and a respect for evidence. And he suggested that the natural world, properly understood, offers wonders enough to satisfy any curious mind without the need for manufactured mysteries built on misrepresented facts. And so, the Bermuda Triangle, which began as a simple description of a region on a map, became something larger and stranger through a process of narrative accumulation, each writer adding to the structure built by those who came before, until the edifice of legend towered over the foundation of fact that had supposedly supported it. And those who took the time to examine that foundation found it rather less substantial than the stories had suggested. The waters are still there, of course, stretching blue and green beneath the sun, carrying their cargo of plankton and fish and the occasional yacht or container ship. And they are neither more nor less mysterious than any other waters, which is to say that they hold mysteries enough for any oceanographer or marine biologist, but not the sort of mysteries that sell millions of books or inspire breathless television documentaries. Ships still pass through on their way to and from the ports of Florida and the Caribbean, and aircraft still fly overhead on routes between North and South America, and the Coast Guard still responds to distress calls from boaters who have run into trouble. And the world turns, and the waves rise and fall, and the stars wheel overhead at night just as they have always done, indifferent to the names we give to the waters below or the stories we tell about them. And so we return now to the present day, to the Bermuda Triangle as it exists in this very moment, while you lie there growing heavier and more peaceful with each passing breath. The waters between Miami and San Juan and Bermuda continue their ancient rhythms, the Gulf Stream still pushing northward as it has for thousands upon thousands of years. The trade winds still crossing from east to west, as they did when the first European sails appeared on the horizon. But the triangle of today is a very different place from the one that existed even a few decades ago. surrounded now by an invisible web of technology that monitors and tracks and records with tireless electronic patience. Satellites orbit high above the Atlantic, their sensors sweeping the ocean surface in regular passes, measuring sea height and temperature and the movement of currents with a precision that would have seemed like magic to the sailors of previous centuries. Every commercial vessel that crosses these waters carries transponders that broadcast their position continuously. Their signals picked up by receivers on shore and in space, creating a constant digital record of where each ship travels and when. Aircraft flying over the triangle are tracked by radar systems that can follow their progress across hundreds of miles, their flight paths appearing as small moving dots on screens in control towers and monitoring stations throughout the region. The Coast Guard maintains stations along the Florida coast and in Puerto Rico and on the islands scattered throughout the Bahamas, their crews ready to respond to any emergency, their rescue helicopters and cutters positioned to reach vessels in distress within hours rather than the days or weeks that such rescues might have taken in earlier times. This transformation has happened gradually, one technological advance building upon another, until the triangle has become one of the most closely watched stretches of ocean on the entire planet. When ships transit these waters now, their owners and operators can follow their progress in real time on computer screens thousands of miles away. When aircraft fly the routes between the mainland United States and the Caribbean islands, air traffic controllers maintain constant communication, tracking each plane's altitude and speed and heading with instruments that leave very little to chance or uncertainty. The age of vessels simply vanishing without explanation, without any trace of their passage or any hint of their fate, has largely given way to an era of documentation and monitoring that makes such complete disappearances increasingly rare. Accidents still occur, of course, because the ocean remains a powerful and unforgiving environment, and mechanical failures and human errors and unexpected weather can still claim lives despite all our technological safeguards. But when something goes wrong in these waters today, we usually know about it quite quickly, and we can usually piece together at least a general understanding of what happened and why. Yet, for all this monitoring, for all these satellites and transponders and radar systems and Coast Guard stations, the ocean itself remains vast and deep in ways that humble our attempts at complete understanding. The technology we have developed allows us to watch the surface of the sea with remarkable precision, to track the movements of ships and planes and storms with an accuracy that previous generations could never have imagined. But the ocean is not merely a surface. It extends downward into darkness, layer upon layer of water pressing upon the layers below, until at the deepest points the pressure becomes so immense that it would crush most human-made vessels like empty cans. And this vast vertical realm, this three-dimensional wilderness of water that covers more than 70% of our planet's surface, remains in many ways as mysterious and unexplored as it was when the first humans ventured out upon it in their simple boats. According to the National Oceanic and Atmospheric Administration, approximately 80% of Earth's ocean floor remains unmapped by modern high-resolution methods. This statistic bears repeating in a different way, because its implications are easy to overlook. We have mapped the surface of Mars in greater detail than we have mapped the bottom of our own oceans. We have sent robotic explorers to photograph the moons of distant planets, while vast stretches of seafloor right here on Earth remain unseen by human eyes or human instruments. The reason for this disparity is not indifference, but rather the profound difficulty of exploring the deep ocean. Light penetrates only a few hundred meters into seawater before it is absorbed entirely, which means that most of the ocean exists in permanent darkness. Pressure increases by roughly 1 atmosphere for every 10 meters of depth, which means that at the bottom of the deep Atlantic, the pressure can exceed 500 times the pressure we experience at sea level. Building instruments and vehicles that can withstand such conditions, that can navigate in complete darkness at crushing depths while transmitting data back to the surface, represents one of the most challenging engineering problems humanity has ever faced. The discoveries that have emerged from deep-sea exploration suggest just how much we have yet to learn. Scientists continue to find new species in the deep ocean with remarkable regularity, creatures adapted to conditions so extreme that their very existence challenges our assumptions about what life requires. Hydrothermal vents on the seafloor support entire ecosystems that derive their energy not from sunlight, but from the chemical reactions between superheated water and minerals from the Earth's crust. Fish with bioluminescent organs create their own light in the eternal darkness, using chemical reactions to produce ghostly glows that serve purposes ranging from finding mates to luring prey. Giant squid, which for centuries were dismissed as sailors' legends, have now been photographed and filmed in their natural habitat, confirming that the deep ocean does indeed contain creatures of extraordinary size and unfamiliarity. Each research expedition that descends into the abyss seems to return with footage of organisms never before documented, life forms whose names have not yet been assigned because science has not yet had time to study them properly. The seafloor itself continues to reveal features that surprise even experienced oceanographers. Underwater mountains rise from the abyssal plains, some of them taller than any peak on land, their summits still thousands of meters below the surface. Vast underwater canyons cut through the continental shelves, carved by processes that scientists are still working to understand fully. Entire mountain ranges extend along the ocean floor where tectonic plates are pulling apart, their volcanic ridges creating new seafloor material in a process that has been shaping our planet for billions of years. In some regions, the seafloor is covered with mineral formations called manganese nodules, potato-sized lumps that grow over millions of years as metals precipitate slowly from the seawater above. In other areas, strange formations of methane ice called clathrates lie just beneath the sediment, their stability dependent on the precise balance of pressure and temperature that exists at those depths. These are not exotic features found only in remote corners of distant oceans. They exist throughout the world's seas, including in the waters of the Bermuda Triangle, which touches the deep Atlantic basin where some of these phenomena occur. The triangle itself encompasses a remarkable range of ocean environments within its loosely defined borders. Near the Florida coast and throughout the Bahamas, the waters are often shallow and clear, their pale turquoise color reflecting the white sand and limestone that form the seafloor just meters below the surface. These are the waters where the underwater aircraft and scattered debris of lost vessels sometimes appear, visible from the surface on calm days, mysterious shapes glimpsed through the translucent blue. But as one moves east and south away from the continental shelf, the seafloor drops away rapidly, plunging thousands of meters into the abyssal depths of the Atlantic basin. The Puerto Rico Trench lies along the southern boundary of the triangle, and this submarine canyon contains the deepest point in the Atlantic Ocean, a place where the seafloor lies more than 8,000 meters below the waves. These are depths comparable to some of the deepest places on Earth, depths where the pressure would crush a human body in an instant, where no sunlight has penetrated for billions of years, where the sediment that blankets the bottom has been accumulating one microscopic particle at a time for longer than humans have existed as a species. The triangle also encompasses some of humanity's busiest shipping lanes, corridors of commerce where cargo vessels and tankers and cruise ships pass in steady procession, their wakes crisscrossing the same waters where sailing ships struggled against contrary winds centuries ago. The ports of Miami and Fort Lauderdale and San Juan and the dozen other harbors that line these coasts handle cargo measured in billions of tons each year. And much of that cargo passes through the triangle on its way to or from destinations around the world. Cruise ships carrying thousands of passengers depart regularly for island-hopping itineraries through the Bahamas and the Caribbean, their routes tracing paths across waters that once seemed dangerous and uncertain to earlier generations. Container ships stacked high with goods from Asia and Europe transit these lanes on their way to American ports, their navigation systems plotting courses with electronic precision that leaves no room for the confusion and uncertainty that plagued ships in earlier eras. This is one of the great contradictions of the triangle as it exists today, that these waters are simultaneously among the most traveled on Earth and among the least understood in their deeper dimensions. And drifting through all of this, at the eastern edge of the triangle where the boundaries grow vague and the open Atlantic stretches toward distant continents, lies the Sargasso Sea with its floating mats of golden seaweed. The sargassum still grows here, as it has since before humans first crossed this ocean, its branching fronds supporting their small gas-filled bladders, its tangles providing shelter for the crabs and fish and shrimp that have adapted to life among its drifting forests. The great subtropical Gaia still rotates slowly around this calm center, the currents that define the Sargasso's boundaries continuing their patient circuits as they have for millennia. Satellite images now allow scientists to track the distribution of sargassum across the Atlantic, to measure how its abundance changes from season to season and year to year, to study the ways it responds to shifting temperatures and nutrient levels. But for all this monitoring, the Sargasso retains its essential character, that strange stillness at the heart of the ocean's motion, that golden wilderness adrift upon blue water. There is something worth considering as you lie there, breathing slowly and settling deeper into rest, about the relationship between mystery and understanding. We live in an age of explanation, an era when the answers to most questions can be retrieved within seconds from the devices we carry in our pockets. The mechanisms of weather and disease and gravity and light have been revealed through centuries of patient investigation. And this knowledge has transformed human life in ways that would astonish our ancestors. The Bermuda Triangle, which once seemed to present an impenetrable enigma, has yielded most of its secrets to careful research and analysis. The disappearances that once seemed supernatural now appear as the natural consequences of geography and weather and human error. Tragic but explicable, no more mysterious than accidents that occur on highways or in mountains or in any other environment where humans venture into conditions that can overwhelm them. Yet mystery itself serves a purpose in human experience, a purpose that perhaps should not be dismissed too quickly. The unknown invites curiosity, and curiosity drives the investigations that expand our understanding. The unexplained reminds us of the limits of our knowledge, and this awareness of limits can foster a humility that serves us well. When we gaze at the ocean and recognize that vast stretches of its depths remain unmapped, when we acknowledge that creatures we have never seen swim through waters we have never visited, we are participating in one of the oldest human experiences, the recognition that the world is larger than our comprehension of it. This is not ignorance, but rather a kind of wisdom. The understanding that even in an age of satellites and sensors and databases, the universe retains dimensions that exceed our grasp. The Bermuda Triangle no longer frightens seasoned sailors or experienced pilots, who know that these waters present challenges but not curses, difficulties but not supernatural malice. The cruise ship passengers who gather on decks to watch the sunset as their vessels cross this region feel no particular anxiety about the triangle's reputation, which has become a kind of joke or a piece of nostalgic entertainment rather than a source of genuine fear. The pilots who fly the routes between Miami and San Juan focus on their instruments and their communications, untroubled by legends that belong to a different era of understanding. This demystification is, in its way, a triumph of human reason, a demonstration that careful investigation can dispel shadows that once seemed impenetrable. But the ocean remains vast and deep and indifferent to our categories and explanations. The stars that shine tonight above the calm Atlantic are the same stars that Columbus watched from the deck of his small ship more than 500 years ago. The same points of light that have reflected on these waters since before humans existed to wonder at them. When the sea is calm, as it sometimes is in these subtropical latitudes, the boundary between water and sky can seem to dissolve, the stars appearing both above and below in a seamless sphere of darkness and light. On such nights, it is possible to imagine oneself suspended in space, floating between two infinities, the depth of the ocean below and the depth of the cosmos above, both extending beyond any scale that human intuition can grasp. The ocean has always been larger than our understanding, and this has always been part of its power over human imagination. The first sailors who ventured beyond sight of land must have felt this enormity in their bones, the awareness that they were very small creatures adrift on something very large, dependent on their skill and their luck and the mercy of forces they could not control. Modern technology has reduced our vulnerability in many ways, has given us tools that would have seemed miraculous to those early mariners, has made ocean crossings routine rather than heroic. But the ocean itself has not changed. The same Gulf Stream that carried Columbus's ships toward the unknown still flows northward through these waters. The same deep Atlantic that has swallowed thousands of vessels over thousands of years still extends downward into crushing darkness. The same stars still shine, and still reflect, and still invite the mind to wander into contemplation of distances and depths that exceed all our instruments. And so we leave the Bermuda Triangle as we found it, neither more mysterious nor less, merely better understood in some respects, while remaining unfathomable in others. The ships continue to pass through, their lights visible on the horizon like moving stars. The aircraft continue to fly overhead, their running lights blinking steadily against the darkness. The seaweed drifts, and the currents flow, and the deep creatures pursue their lives in the blackness far below. Nothing supernatural haunts these waters, but something ancient does. The same ancient vastness that has always been here, patient and immense, older than humanity, and certain to endure long after our brief moment of wondering has passed into silence.